All right, chemistry class. We are now starting chapter 2. You've finished chapter 1. The first section in chapter 2 is about the scientific method. And this section covers the scientific method and its component activities such as observing, collecting data, formulating and testing hypotheses, as well as theorizing. So there are going to be some learning goals like normal. Let's get those out in the open. First, I want you, at the end of this section, to be able to describe the purpose of the scientific method. Scientific method is not something that we make you learn in every science class just because we want to. There is a reason. Number 2, I want you to be able to distinguish between qualitative and quantitative observations. And lastly, for this section, I want you to be able to describe the differences between hypotheses, theories, and models. So the scientific method, it is a series of steps that are to be followed during a scientific investigation. Remember, anything that is science is a systematic inquiry. So systematic means that there are some steps that need to be followed. And it should be pointed out that even though this inquiry is very systematic, it goes by steps and a particular progression, it's not a static thing. Okay? Depending on the type of investigation you're carrying out, your scientific method may be different from someone else's scientific method, depending on what you're investigating, how you're investigating it, what instrumentation you're using, or even what timeline you're on. Your steps may vary. The important part, it's a logical problem-solving technique. It's designed to help you reach a conclusion based on evidence. And this systematic inquiry, this scientific method, is not that old. The first people to describe it, it's kind of jointly at the same time, Galileo and Sir Francis Bacon. So the scientific method, definition for you, it's a logical approach to solving problems by observing and collecting data, forming hypotheses and testing hypotheses, and formulating theories that are supported by data. This is where the natural sciences really start to move away from or distinguish themselves from older sciences like philosophy. It's logical, that's the same, that's what philosophy used to do. But collecting data, the old philosophers used to think that any instrumentation that you had to use indicated some sort of weakness on the part of your mind. But in natural science, we have to collect data and use that data to inform further investigations and our ideas about the world around us. So an observation, we start by an observation as the recognition of a problem. Some people don't like to use the word problem, they like to use the word question, because sometimes what you're looking at isn't a problem. It just brings up a question. So it's a recognition of a problem or a question. It needs to be a visible or provable fact. Okay? If you're going to investigate something, the fact that something exists needs to be showable, needs to be provable. From that observation, some sort of question arises, a problem statement. And a problem statement is a question that compares variables. Here's where people make mistakes when it comes to a problem statement. It has to have two variables. You have to compare two things because this scientific method that furthers natural science has to be able to, one, generate data, and that data needs to be analyzable. And so how we ensure that happens, we have two different variables that we compare. My example here is, does the amount of salt water affect the boiling temperature of water? So if I have fresh water, will it boil at a different temperature than salt water? And if I continue to add salt to that solution, will that affect the temperature? Or sorry, the boiling point. Hypothesis is another misunderstood term. It's a proposed explanation of an observation. Okay? It's not anticipating what will happen. It's anticipating the explanation. Okay? Some people refer to it as an educated guess. However, it has to be testable. If you're making up ideas or trying to explain why something's happening, but you can't test that idea, then it does not fall under the definition of a scientific hypothesis. It is a statement, it's not a question, that expresses the expected answer to the problem statement, what you think the results of the experiment will show. So it's a statement about about why and what you expect. Okay, so you're looking forward, you're looking at what you know based on your observation, what you expect to happen, and why. To continue my example, if you increase the amount of salt added to the water, the boiling temperature will also increase because, and you would go on to explain why you thought that was the case. But here again, we're explaining the observation, or at least attempting to explain the observation. Once we've established a hypothesis, we move on to the experiment phase. An experiment is any organized procedure used to test a hypothesis. Now, this does not have to occur in a lab. This does not have to occur, with you wearing like a big white lab coat and goggles. You can use an experiment that is as simple as kicking a rock. Okay, anytime you test an idea that you have, that's an experiment. For completeness, we need to include that it's going to involve measurement and data collection. And in order to test the hypothesis, which was comparing two different variables, we need to manipulate those variables and figure out how those variables are changing quantitatively. It is a planned way to test the hypothesis. It's not by accident. You need to put in effort to design your experiments in order to attend to those two variables. It needs to be a way to collect data and determine the value of the dependent variable. We'll define that on the following slides. And then it compares the independent variable, again, that's coming on future slide, to the dependent variable. So you're comparing those two variables that you established in your hypothesis. And you should keep in mind, you can only test one dependent variable at a time, one thing at a time. So that may mean, and often means, that you need to perform any given experiment multiple times. So any quality scientific experiment is going to have at least three parts to it. You're going to have a control or a standard for comparison. You're going to have variables, and you're going to have constants. Now, there are two types of variables, independent and dependent. The independent variable is something that changes completely unrelated to anything else because you, the scientist, change it. You manipulate it, you change it on purpose. It's the variable that you are investigating. Okay? And because you set this variable, you know its value, you know what its value is. Once you generate other data, you can use that as a starting point of comparison. An example here, does the amount of salt in water affect the boiling temperature of water? We know how much salt we add to each volume of water before we boil it. So the salt is the independent variable. We're manipulating that. We are setting that amount. As opposed to the dependent variable, it's a variable that changes depending on other factors. Okay? It's the variable that we're trying to investigate. It's the variable whose value we do not know before we start. In the boiling salt water example, we do not know the boiling temperature of water once the salt is added. We have to actually run the experiment in order to determine that value. There are also constants. People forget about these quite often. Constants are things that don't change throughout the experiment. They remain the same the entire time. For example, we would not change the brand of salt or the amount of water or from where we get the water. Okay, we'd want to keep all those things the same for each round of the experiment. Because if we did change the brand of salt, okay, if we changed it from sodium chloride to potassium chloride or use a different kind of salt, we would be adding another kind of variable to the study, and we want to keep those variables limited to 2. After your experiment, you need to analyze the data. Okay, you're not done. You don't just get to look at the experiment and understand everything about it. You have to collect your data, then analyze it. Now, there are 2 types of data. Again, this is one of your learning objectives: quantitative and qualitative. All right? Quantitative refers to a quantity, something that can be described by a number. Examples of a quantitative value would be temperature. Okay, there is a number associated with temperature. You can calculate increases in temperature, decreases in temperature, as well as boiling point and melting point, things that are associated with some sort of numeric value. As opposed to qualitative, a quality about something, something that you see. For example, color is a qualitative characteristic. The ability of a metal to be ductile or a non-metal to not be ductile, that is a qualitative observation. And then data that are collected in this manner, typically represented using graphs, popular ones being pie charts, bar graphs, and line graphs. You reach a conclusion. After you've analyzed your data, you present your findings of the experiment and what the data shows. Whether or not you have to abandon your hypothesis or whether it's confirmed or not, it has to be based on the data. You cannot insert some sort of caveat to say, my hypothesis was this, my data suggests something else. However, I'm still going to go with my hypothesis. The data needs to guide your conclusions. And it should be pointed out that if your hypothesis manages to be rejected, it's not a bad thing. People mistake that. If you do not come up with a hypothesis that is accepted or supported by the data, young scientists tend to think that that is a failure. It is not. You have learned something, and you now know how to either proceed, or now you understand that this line of investigation is not fruitful at this time. You can go do something else. But there's always going to be something learned, even if your hypothesis is rejected. This is one thing that we don't learn about in high school all that often, but communication. Okay, when scientists work together, they very often come up with something that is valuable, but they have to communicate that to the world. Once you get into a college science class, they're going to talk about publishing papers. Okay, they're going to publish papers in peer-reviewed journals on the internet. They're going to be going to different seminars, speeches, presentations, things like that. Science isn't made, at least in this day and age, for just to be happy that you've learned something. You need to share that with the world so that other people can benefit as well. I do want to point out the difference between observations and inferences real quick. An observation is something that you can confirm, something that is very easily shown to be true or be a fact. It's a piece of information about the world around you, something that exists or events that have occurred. You're just stating a very understandable fact. Whereas an inference is an abstract or general idea that's derived from a very specific set of circumstances. An inference is going to be something like an idea, a thought, concept, a notion, or an opinion that is not readily knowable to everyone at all times, not something that would be obvious, for example. Theory. Okay, theory, again, is something that's misunderstood pretty commonly. A theory is a well-tested explanation for a broad set of observations. Remember, your hypothesis is an attempt to explain an observation. When a hypothesis has been supported several times, we indicate well-tested here, it can be upgraded to a theory. And by well-tested, hundreds of times by different people at different times, a hypothesis will be upgraded to a theory. Theories often use these things called models. And a model is something that allows you to make a prediction because it explains why you've observed things in a particular fashion. It's a line of reasoning, statement about reality, that if it is true, allows you to make inferences about situations that have not been tested. Right? Well, if this is true, and this is the explanation, then if the second situation happens, we should observe this, that, or the other thing. But something that allows you to move forward in your investigation. As opposed to a law. Okay? A law is a statement that summarizes the results of observations but does not explain them. A theory or a hypothesis will attempt to explain them. A law, truly speaking, is just a statement about what happens. Okay? Just what happens. I did this, and then this happened. When this happens in the world, this tends to follow. Okay? A law will be changed or abandoned when contradicted by a new experiment. Just one. Okay? One thing that people really mistake about science is that we prove things in science. We do not prove things in science. We actually disprove them. Okay? You can support an idea with 1,000 experiments, but all it takes is to be shown incorrect once and substantiated, and that idea has to be abandoned. Like I mentioned before, the order of the steps can vary and additional steps can be added depending on the type of investigation, the group of people who are involved in the investigation, the instrumentation, or even the timeline or budget. I'm going to leave you with this. This is a quote from Albert Einstein. "No number of experiments can prove me right. A single experiment can prove me wrong." Okay? It is not a bad thing to be wrong in science. As long as something is learned, that was the point to start, and that's what you've accomplished. Right? Just to recap, I'm hoping at the end of this section, you will be able to describe the purpose of the scientific method, distinguish between qualitative and quantitative observations, and describe the differences between hypotheses, theories, and models. All right, I will see you next period.